All right, kids, did everybody get notes there? Everybody have them? All good here? Good.
Biscuit joints.
All right. 10.3, what's our title, kids?
Using chords.
Remind me what a chord of a circle is again.
It's the segment where the endpoints are on the circle.
The endpoints are on the circle. So there's 2 points on the circle. We connect a line segment between the two of them. We call them a chord. What's the name of the chord that passes through the center? Diameter. So we're going to start looking at properties of chords today, kids. Our essential question, what are 2 ways to determine when a chord is a what?
Diameter.
Diameter of a circle. We're going to talk about how do I know that this is a diameter and how it comes about. I mean, 2 reasons for that today, okay? All right. Goals. Actually, there's only one goal that we really need to understand or accomplish today to answer that question. So who wants to volunteer to read my goal up there?
Use chords of circles to find lengths and arc measures.
Okay, we're looking for lengths and arc measures. We're going to be looking at lengths of chords and arc measures, and we're going to use those to determine if a chord is a diameter or not. Okay? So I think vocab-wise, most of this ought to be prior knowledge to you. Okay? We'll sketch them up here again just to make sure we can get a good visual of them. But the first vocab word I have up here is chord. Volunteer to read that definition, please.
A chord is a segment with endpoints on a circle.
So again, if I have a circle, then a chord would be a line segment that goes from one endpoint to another endpoint, and the endpoints are on the circle. Now the way I've drawn that, is that a diameter or not? Why is that not a diameter?
It doesn't go through the middle.
Okay? So if I jump down here to diameter, you know what that is, so we'll just make another quick sketch of that. Diameter is a chord that passes through the what? Center. So if this is my circle right here, whoops, don't want no lips. Is that better? And the diameter is going to pass through which point? Looks like I missed a little bit there, doesn't it? Is that better? Maybe. You get the idea. You get the idea, right? That's the best I can do. And then, guys, arcs. Arcs are parts of the circle established by what? Okay? If I had this drawn right here, kids, if I had a circle right here, and I had a chord in it right here, like so, is the major arc above or below that? And where's the minor arc established by that? Below it, okay? So I'm going to say that down here is my minor arc. And then up here between these 2 points is your major arc. Okay? So some definitions. We need to know what a chord, an arc, and diameter are today. I think you know this already, okay? But to put them in terms of an illustration, that's where we're at. Okay, we've got some theorems we need to understand today. Got some theorems we need to understand. Let's start with the congruent corresponding chords theorem. Let's read through these and see if we can't provide an illustration to these, all right? The congruent corresponding chords theorem states the following. It states in the same what? Or in? So we're talking about circles the same size or just one circle. 2 minor arcs are what? If and only if they're. So what they're saying is this. If I have a circle and I label a chord right here, let's just make a chord that goes like so from here to here. And let's do one from maybe here to, I didn't want to do it that way. Maybe here to here. Gosh dang it. Maybe it looks like that. Okay? So if I say that this is a point A, and this is a point B. And I'm going to call this point up here C. And I'm going to call this point D down here. Congruent corresponding chords theorem states that in the same circle, two minor arcs are congruent if and only if their corresponding chords are congruent. So this is saying if AB right here, this length AB is congruent to what? Okay, if those two marks are congruent, then what this is telling me, kids, is that the arc measure from A to B is the same as the arc measure from what to what? Okay, so this is saying that the minor arcs, this tells me that if this is the diagram that's given here, if this diagram is given, then what we can say is arc AB is congruent to what, kids? Okay, you understand what I'm talking about there? So, oh, why is my computer doing this? Did everybody just see that happen?
Yeah.
Yeah.
Black looking back off.
Yeah, blacked out and then came back on. Okay. I wonder if that's going to do that all day. It's been doing that all day. Okay. Okay, so if you have two chords that are equal in a circle, what's true about the minor arcs formed from those two chords that are equal? They are equal to each other. We call them corresponding congruence chord theorem. Okay, next one. What word do you see here?
Perpendicular.
Perpendicular means what angle has to be formed?
90.
And then you see this word bisector. It means it's going to take a segment and cut it in half. So we're going to cut a segment in half at 90. It says perpendicular chord bisector theorem says if a diameter of a circle is perpendicular to what? Then the diameter does what? And its arc. So what I'm saying is this. So let's say that we have a circle that looks like this with a radius. So I'm sorry, let's get a diameter in there. Let's put a diameter in here like so. Okay, that looks pretty good for a diameter, doesn't it?
Yeah.
They're telling me right here that if I have a chord that goes through the diameter and forms, let's draw it just like that. Okay, let's label this A up here, and let's label this B right down here. We'll call our diameter C to D. Is that okay, kids? What should we call the circle? You want to call it P today?
Looks like the Smash Bros.
Looks like what?
The Smash Bros. thing.
Really?
Golden State Warriors.
Okay then.
If it was
Golden
on-
State Warriors?
You just draw the bridge.
I see it. They got beat last night, didn't they? I think they blew like a 31-point lead or something. Wow. Wowzers. Well, my team's not in playoffs, so I guess I could care less.
I think they're number one. They were.
What has to be true right there? The diameter and the chord have to be what? Okay, it says if the diameter is perpendicular to a chord, then it does what?
Bisects the chord and its arc.
Okay, so I'm going to put a point right down here, kids. Let's maybe call this T right here where the chord and the diameter intersect. Okay, what this is telling me, two things. If you have a diameter that's perpendicular to a chord like this, then that tells me that AT has to be equal to what? Segment AT would be equal to segment what? AT would be congruent to. Okay, so two things that happen here. Segment, that's a line segment. AT is congruent to segment TB. And it also says it bisects the arc. Arc AB gets bisected into two congruent arcs. So this means AD would be the same as what? DB. Okay, so this also means that AD, arc AD, is congruent to arc what again? So if I have a diameter perpendicular to a chord, the diameter perpendicularly bisects the chord, and it also bisects the arc. Okay? Does that make sense? So maybe I should put some drawings up here or some tick marks in here. If I put tick mark, AT would be congruent to what here? TB, and then if I looked at arc measures to be congruent, maybe I just put a double tick mark here and a double tick mark there. That's what's going on there, okay? This only works if a diameter intersects a chord at what angle? 90 degrees, okay? Then it'll bisect that stuff, okay? All right, now, guys, do I expect you to remember the names of the theorems? I do, but do the visuals help you understand what the theorems are saying? Okay, so refer back to the names of these if you see these types of things. All right, last one. Guys, last one's kind of working backwards. It's the perpendicular chord, bisector, converse. Converse teaches hypothesis and conclusion and does what? Flips it. So this says if one chord of a circle is what? Perpendicular bisector of another chord, then the first chord is the what? So they're saying this right here. What they're saying then is this. They're saying, hey, if this is the picture, here's your circle, and they say if this is a situation where, well, I don't know, here's a chord. Let me draw a chord from here to here. You guys okay with that chord? Then if another chord bisects this perpendicularly, then this chord must be a...
Doesn't it have to be the middle, right?
I'm sorry?
Like the second chord doesn't have to be the middle, does it?
Grace, say that one more time for me, buddy.
Yeah, well, if it's gonna be perpendicular,
So, yeah, okay,
Yeah,
yep,
obviously it's gonna be straight, but does it have to go through the diameter?
yep.
well, it's gonna have to be
Yep.
diameter.
They're saying this, oops, they're saying if two chords are perpendicular in a circle, if two chords are perpendicular in a circle like this,
Does one of them have to be the diameter?
one has to be the diameter, yep. So let's label these right here. Let's call this, well, it's telling us the perpendicular what, actually? It's saying that this is perpendicular and this distance right here is equal to that distance, okay? So what this is saying, if this is your setup right here, if this is your setup right here, then what must be true about CD? If I have two chords in here that are perpendicular such that one chord perpendicularly bisects the other chord, then CD must be my what? CD must be a diameter here. Okay, so 3 new theorems. I don't expect you to memorize the names, but can you go ahead and take the illustration with the explanation and put an idea together here? Okay, so let's try and enact these real quickly. Let's put them into play and see what we can get. I want to make sure you have everything down as I do up there on your notes. Everybody cool there? Did I give you notes? Make sure you get this down, buddy. You're wasting time. Okay. Make sure you get that from someone, okay, Leighton? Let's try this. Example number 1, using congruent chords to find an arc measure. It says in the diagram, circle P is congruent to what, kids? Circle P and circle Q, same circle, okay? It says FG and what? They are the same. It says the measure of arc JK down here, how many degrees? 120 degrees. So if JK is 120 degrees, we need to find what? Well, this is the corresponding congruent chords theorem. If this is 120 degrees at JK, then what must be true about GF if these chords are the same in the same circle? Measure. What is it? Arc FG must be equal to what? 120 degrees. Okay. I'm just going to go back right here, guys. Basically, it's this theorem right here that says if you have the same chords, if you have the same chord lengths, then minor arcs must be the same. So is it okay if I call this the congruent corresponding chords theorem?
Yeah.
Or the CCCT? Can I abbreviate CCCT for this? How are we going to abbreviate this one? And how about this one? PCDC. Okay. So this first one would be by
CCCT.
mm-hmm. Corresponding congruent chords theorem. Okay. Let's try another one. Next one states using a what, kids?
Diameter.
Diameter. Ooh. Well, which segment is the diameter?
Oh, whoa, JL.
JL. And HK is a
Chord.
chord. But here's the deal, kids. That diameter, JK, cuts through this chord and forms a what? Okay, so it says find the distance from K to H. Well, guys, if K to N is 14, what must be true about H to N? So if I want to find the length of K to H, what are you going to do? 14 and?
14.
Which would be? Yeah. Now, kids, it says find what?
HLK.
We got to find the measure of HLK, but don't we have to use these up here somehow, kids?
That equals 180.
Ooh, be careful.
That doesn't equal 180.
That arc's not going to be 180 because I could
How are we
draw.
supposed to know what it is then?
Well, here's the deal. Remember that if you have a perpendicular bisector through a chord, it bisects the segments, but it also bisects the...
Oh, 127 minus x is going to equal 2x.
Yeah, so for this one right here, isn't this arc right here going to equal this arc? And if I can find this arc and this arc, doesn't that allow me to find the rest from H to L to K down here?
Yeah.
Okay, so let's do that. We would know that 2x minus 8 has to equal what, kids, in part B? 127 minus x. So I'm going to add an x to both sides. Is that okay to do? So this will become 3x minus what?
8.
Equals?
127.
Next step.
Plus 8.
So I've got 3x equal to, I don't know, you tell me, 135, is that right?
Yeah.
Now divide that side.
Equals 45.
Now guys, if it was saying solve for x, would I be done?
Yeah.
I would be, but are we done?
No.
Okay.
No, we've got to figure out what these angles are. So right up in here, if I can find this measure and this measure, add them together, wouldn't I subtract that from 360 to find from H to L to K here? Okay, so help me with this part right here, kids. Plug in 45. What's that make this arc measure right here? What's 82? Plug in 45 up here. What's that make this measure?
82. So it's 161.
Okay, so all the way around there from H to J to K, that's 164, isn't it? But I want this bottom part, H to L to K. So angle HLK, or arc, I'm sorry, measure of arc angle HLK would equal 360 minus what? Minus 164, which makes that, boy, my north of Highway 3 math skills, I think that's 196 degrees, isn't it?
Yeah.
That's kind of a toughie. A lot of stuff going on there, okay? Again, the idea being this, though. If a diameter is perpendicular to a chord, then it must bisect this perpendicular, which makes H to N congruent to N to K, but it also makes these arcs the same up here. Okay. Any questions about that one? It's kind of a tough one. I'm sorry? Is that a no? What, we ourselves?
Yeah.
Maybe I just haven't had enough coffee yet.
I'll talk to myself.
All right. I like example 3. What are we using here, kids?
Perpendicular bisect.
Okay, this is kind of a, you might want to sketch this in here. It says a telephone company plans to do what? That is the, from the, what is going on here?
The computer's not doing it.
Computer is doing it. It's the computer. Oh, the computer didn't go off?
No.
It was this thing?
Yeah.
Probably made by the Ford company. That's why it doesn't work. Telephone company plans to install a cell tower that is the same distance from the centers of 3 towns labeled P, Q, and R. Where should the cell tower be placed? Guys, this is very simple. All you need to do is draw perpendicular bisectors between a segment P to Q and Q to R. Okay? So what I'm going to try and do is say is, well, you're going to put a perpendicular bisector right about here. What angle did I form with the black line I just drew?
90.
And what looks true to be, let's call this maybe M right there. What looks to be true about PM and QM?
Yeah, about the same.
They look about the same. What else do you think we're going to do now? Draw a perpendicular bisector from what to what?
But they're not really there,
Okay, so I'm just going to draw a perpendicular bisector between Q and what?
so that'll be straight.
Okay, here's the deal, kids. Take a look at this. I'm about here. What do you notice about my distance from where my finger, my thumb, to my index finger is? Let's just check this out. Watch this. This is kind of cool. Does that point look like it's kind of close to the center right there of my circle? Okay. If you want to know where to place that tower so it's the same distance, that's what you would do. Okay? Perpendicular bisectors help you find like the midpoint or the best point of placement so that it's equidistant from all corners, okay? Does that make sense to you? So again, use perpendicular bisectors to find the point that's going to be equidistant from all 3 points. Okay? All right. That's kind of a tough example, but you just, tough example, but visualize it. You can kind of see it there, okay? Good push. All right, one more theorem, kids. It's called the Equidistant Chords Theorem. Kind of hard to read, so look in your paper. Do I have a volunteer that would read that for me?
The theorem?
Yep.
In the same circle or in congruent circles, 2 chords are congruent if and only if they are equidistant from the center.
Now, when I measure stuff from one place to another, it's like I could stand at this point. I'm standing right here. If I put my tape measure down right here on the floor where I'm standing, I say, I'm going to measure to that wall.
So you measure it to the wall, and then
Do I pick one point down there to measure the distance from where I'm standing to that wall, or do I pick multiple?
pick.
Talk to me about the path to that wall. What kind of path would form between my tape measure and that wall down there? Would it
Straight
form?
line.
It's going to be straight. Definitely going to be
Do you
straight.
want it perpendicular?
Huh?
Do you want it perpendicular?
When they talk about equidistant to the center of there, you're always talking about a perpendicular distance. So I want you to understand this distance. The distance that they are talking about, kids. What was that? I heard a whistle.
Jonathan.
What's this mean right here, kids? The distance is always what?
Perpendicular.
Always a perpendicular. The distance is always a perpendicular. Okay? So what this theorem is saying, equidistant chords theorem, is this. An example 4 would be a great example for this. It says using congruent chords to find a circle's radius. It says in the diagram EP is equal to what? Which means EP and EQ are both which distance here? 12 and 12. Okay, so from the center of the circle to the chords, we are equidistant. And I say they're 12 because they form what angle with the chords, kids? They have to form a 90-degree angle with the chord. It says CD is equal to what? And AB is equal to? We need to find the what, kids? This is kind of an upper level problem. Okay? Here's the situation. Understand this. Could I extend this to be a diameter through here, kids? I could, which would mean CQ to CD would be the same. I'm sorry, CQ and QD would be the same. Now, is there a radius drawn in here anywhere at all? Okay. Let's use this theorem first to see if we can't figure this whole thing out. So by this right here, since e to p is 12 and e to q is 12, and they're both perpendicular distances to those two chords, what must be true about the 5x plus 7 and the 7x minus 3? They're the same. So let's solve for x first. That's a dead giveaway. We have to do that. So set 5x plus 7 equal to what, kids? Okay, you guys take a second and solve that. I'll try to beat you. I get x equals what?
Oh, what the heck?
Is my bulb dying in this, kids?
Probably not. I was
Like $800 expensive.
Well, they were.
apartment, that's $800.
X equals a ball is $800.
Yeah, we have one.
I think so. Okay, so what do you guys get x equal to? All right, so that's good. Now, listen up, kids. Once I know x is equal to 5, what's that make this distance from C to D?
32.
32. So C to D is equal to 32. Now, kids, listen carefully on this. It says find the what?
Radius.
I don't have a radius, but I want you to draw this in here, and this is very, very important, so make sure you get this. Do you guys agree that right here I could draw a line from E to, say, C? And this would be my radius R? You guys agree with that? Ooh, what kind of triangle have I formed here?
Right.
A right triangle.
Hey, if this is 12, this whole CD was 32, so what's that make C to Q by this perpendicular chords theorem? C to Q would have to be what?
16.
Half of that 32, which would be what?
Oh,
16.
Ah, so how can about this? Couldn't I say R squared equals
Oh my gosh.
16 squared plus what?
What's 16 squared?
So R squared,
6.
256, will equal 16 squared plus 12 squared. 16 squared is how much again?
136.
256 plus 12 squared, you know that one.
Wait, I'm confused. How is 16? Okay, 15
All
first. Oh yeah, never mind.
Guys, help me, you should know this. R squared is going to equal 400 here. What's the square root of 400, kids? 20. Makes the radius equal to what here? Guys, we're getting into some upper level stuff here. What do you guys think?
This is quite different. This little piece right here.
That one was a toughie, okay?
Wasn't quite like
Well, we had to show that the chords B, A, and CD were equal. Once I established CQ as 16, guys, the tricky part was to draw what in here? Draw the radius in here to understand that we have what kind of a triangle formed here. Yeah. Okay. All right. I want you guys to try the peer evaluation. How many problems are down there? 3? Okay. You guys, I'm going to stop the recording here and get this loading. I want you guys to take about 5 minutes or so and do that.